Our first speaker is Dina Lipkind, right? Ofer? Ofer Tchernichovski was, when he came to be my student, he performed his PhD with me, and he led a group of 30 students in karate. But he said that he has a lot of time, so at the same time he performed a PhD in veterinary medicine. And for quite a long time he did these three things at the same time. And also he decided that it is time to computerize our work, and he insisted to hire a programmer and computerize the tracking of the animals. Until that time, we didn't track. And when Ofer started his first study with infant rats, he performed at home. And since it was not computerized, he took a chinograph or something, and every square in his living room, he marked with a number. And when the infant rat did his exploratory behavior in the room, he marked down all the squares that the rat visited, and this was his first study, which he later computerized. And I think we were the first in the world to have a tracking method for animals. Later on, there was Ethovision and Noldus who took over, so we gave up the tracking because they spent all their effort into it. But we were the first to track animals. When Ofer performed his postdoc in America, it so happens that he went to study birdsong. And the field of birdsong, for 40, 50 years, part of my ethology course was teaching on birdsong. Birdsong started after the initial period of what was called subsong. And this was terra incognita. Nobody studied it because the bird is making some chats or noises that no one could handle. So the study of birdsong for several dozens of years was restricted for the time that the bird already had syllables and connected the syllables into songs. And Ofer was the first to go into this. It's like discovering Africa. I mean, he went into the subsong period and he turned it into a science. So he's the first to take birdsong and to do a morphogenetic study from zero, recording everything that the bird does from the first day, and then analyzing all the data, not sampling the data, but analyzing all the data. And he made a revolution in the field of birdsong learning. Please, Ofer.
So let me start with an Ilan question. What is development all about? So let me cite Tchernichovski, who said that a man is nothing but the shape of his native landscape. But if you think about it a little bit, it's not exactly true. I mean, this is actually me here with my two older sisters. And you can imagine that they influenced me, but I was a bit of a problem to them too. So we should always think about behavior, in Ilan's school at least, as a dynamic interaction, recursive dynamic interaction between the animal and the environment. And this closed feedback loop is what I'm going to talk about today, trying to connect between my early studies with Ilan and my current study with birdsong. Now, as much as it's true to early development, in the later development, these dynamic interactions are also important. And my two intellectual parents are Ilan and Yoav. They were my both PhD advisors. And if people who don't know Ilan and Yoav may wonder, what do they have in common? Statisticians who study methods for controlling false discovery rate and zoologists who study animal movement. But when I met Yoav 30 years ago, he presented himself as a statistician who studied graphical methods and data exploration. And I think that that's probably one of the reasons why he became interested in false discovery rate, because he wanted to explore data hypothesis-free, kind of like, and then you have to deal with that. So Ilan and Yoav had a lot in common. Both of them are explorer of explorations. And of course, my PhD study became just that, trying to describe exploratory behavior. And you know that when you study science, people always tell you, you have to try to control everything, make sure that all the variables are under your control and separated. Ilan had exactly the opposite approach. Instead of trying to look at innate behavior by removing environmental effect, Ilan's idea in teaching was actually look at the dynamic interactions between the environment and the animal and study those in a holistic developmental framework that allows us to really do what Ilan used to call electrophoresis of the behavior that the development does. So that's exactly what I did. My PhD project was about figuring out how to describe the geometry of exploratory behavior. And funny enough, when I moved to birdsong, I did the same thing, trying to figure out the geometry of song development, and I'll try to connect between those two. So here is my PhD tracking system that Ilan mentioned. This is all done on the roof of the zoo here. I built this big arena, watching movies in the drive-in, and letting those rats run every day. And you can see the rat has a home base. It's exploring, it's doing those excursions. And you can see that the animal go out kind of like hesitantly and slowly and run away quickly. So if it got scared, you also see that over time, those excursions expand. So the animal kind of like move on longer and longer trajectories, but keep some of that pattern in place. So this is my first paper with Ilan, the phase-place representation of exploratory behavior. And the idea is quite simple if you think about it. I mean, instead of just plotting the movement of the animal, we wanted to also look at the velocity patterns. So those phase plots, what they show, you see the marker here? So the home base is here in the center, and the positive velocity is away. The animal accelerate and decelerate and accelerate, and it stops. It's kind of hesitant. Again, it stops, and then it kind of gets scared and gets frightened and then run back. So the area under the curve below is much bigger than the area above. Now, when we look at the development of that behavior, we see that this primitive shape of, again, slowly and intermittently away and fast back is evolving into something slightly different. We see longer trajectories, and we see that this pattern persists far away from the home base, but there's much more complexity in the trajectory closer to the home base. And at that point, Yoav and I started thinking about how to understand that phenomenon. And the idea that we came from is that from the animal point of view, the world is hostile. So the home base is a safe place, but there's kind of like a gradient of hostility. And if you think about that just in terms of the physics, when you move up the gradient, then you climb slowly. And then when you go down the gradient, then you go fast. Very simple. But the idea is that there is dynamic interaction between the animal and the environment. Every time the animal explores, it's kind of leveling the field. And once the field starts looking more like that, because of the exploration geometry, then the pattern changes. You can move fast on the way out, but then again, when you go far away, you can go more far away because you climb less potential, so that's why you increase the distance. And again, the pattern of going back quickly persists far away and not close by. So this is my first and only theoretical paper that I did with Yoav, and here you can see the idea of the potential field and the behavior that correspond to that. And in a sense, this very simple dynamic interaction model explained a lot of the complexities of the movements that we observed. So then I moved to work on birdsong, and the question is, can we think about song development as something homologous, as an exploratory behavior, not in local space, but in vocal space? So let me tell you a little bit about birdsong. So first of all, here's a zebra finch song. It doesn't sound so good for you, but that's because you don't know how to hear. So for your ears, it sounds very mechanical, but it's really not. And, but you can hear the repetition, and those repeated units is what we call motifs. Here is one motif, and here's another motif from the same bird. This is pattern that you see over less than a second. And those spectral patterns, as you can see, are extremely stereotyped. And when you look at any adult bird song, that's really what songs look like in zebra finches. They have motifs that have syllable type, like A and B and C and D, and the animal repeat them. So you may kind of consider those to be excursion, as if you do an introduction, and then you see A, B, C, D, one excursion, and then another excursion. But that's kind of boring, because the animal keeps doing the same thing again and again. And here, I want to tell you a little bit about looking at the development. Because when you look at development of exploration, we talked about a primitive structure that evolved through growth and differentiation into something much more complex. And my first studies discovered something quite similar in the song of the zebrafinch development. What you see early on is a repetition of usually one syllable that I call prototype. And the bird only sings one syllable again, like A. Over a very few days, you see differentiation of that syllable, but later on, the song is becoming much larger. So you see here that the motif is about 3 times bigger than that one prototype. And it doesn't look that similar. So the question is, how did that happen? And the answer for that is that when you look at the prototypes, if you look here, for example, in 2 different birds, and you see here 2 repetitions of prototype, you can see that they evolve into very, very different sounds. One of them here, the first one, looks similar to the prototype, but the second one looks very different. And here it's the other way around. The second one may look similar, but the first one looks different. And when you look developmentally, what you see is that the prototype differentiates slowly into 2 different creatures. And the challenge was to try to describe that in a way that, as Ilan presented earlier, has to be continuous and dynamic. So when we look at acoustic features of every syllables, which can be described simply as the duration, the pitch, all kind of simple acoustic description of how it sounds like, and if you record everything, then every syllable can be automatically reduced into an array of features like that, like the pitch and the duration and so forth. And now if you look at the entire development, you have about 1 million or 2 million of those. And all you have to do is to look at them. But you don't live long enough to do that. So you have to figure out another way of doing that. And here comes the descriptive model. So the idea is that if you just look at those as dots, so that every dot here is a syllable, where you look at, say, 2 features, duration and pitch or whatever, and you just plot, say, 1,000 of those dots, then you have an image. And then if you slide that window over development, over the 2 months of development, you can show it as a movie that shows you the entire development in a minute. And that allows you to actually observe the morphogenesis of behavior. And we look at it in 2 ways. One of them, what you see here on your right side, on your left side, is just the scatter plots. And the clusters you see here are simply what we call syllable types. But you can take the same data and connect the dots. And when you connect the dots, then you get something like a phase plot. You get a trajectory of the singing behavior. So let me show you quickly a movie of song development from the beginning of time when the bird starts doing the first sub-song to the time the bird is making mature song. So the early sub-song, the song looked like a cloud like that. So there are no syllable types, as Ilan say, nobody knows how to look at that. As the bird is learning, and if you look at that kind of cloud, you see that clusters start emerging, like galaxies start emerging in that amorphous cloud, and those clusters start moving away from each other, and new ones are starting to be generated from previous ones. For example, if you look at this guy here in the bottom, right here, at the bottom, you see it's become pregnant, and another cluster starting to emerge out of it. And this is really the process of differentiation of sounds. Here you see the same data with clusters as numbers, as colors, and you can see that the green guy is emerging out of the pink guy, the suite repeatedly like that. And here is the trajectories. And again, you can see a growth It goes from one line into two lines and then three lines that separate from each other. And you can see how smoothly this differentiation of morphogenesis goes, like an embryo that develops more and more layers. This is another bird. And look again, you can see how the clusters start emerging. Here they go up, and then you can see the one on your right differentiating into two different clusters, and the same thing happens. You can see it again and again. The same thing happens on the one on the left. It goes up, and then two creatures emerge out of that. And if you look at this data also as trajectory, again, you can see something look like a triangle, and then there's a piling off of another structure from it that create more and more trajectories on top of that one. So that's kind of like descriptive model really allow us to look at the differentiation of the sounds. And now you ask yourself, okay, well, when I talked about the rat, I told you that the development is really dynamic interaction between the animal trajectories and the environment. What kind of dynamics happens here? Well, nothing. If you think about it, what we did, the bird was imitating a song that it heard, and it didn't have any influence on that, right? It just imitated that. So how can we separate between the environmental effect, the song, and the morphogenesis? Well, the simplest thing to do would be not to give the bird any song to imitate. That would be against Ilan's approach, and it won't work. If you do that, if you give the bird nothing, you get nothing. If there's no environment, there's no behavior. So I thought about it at the time, and we came up with an idea of doing something that allows us to look at dynamic interaction of environment and birdsong by playing a trick on the bird. We presented birds with a vocal robot that sing to the bird and train the bird, but we trick the bird to think that he's being trained, where in fact, what the robot sings to the bird is a recording of the bird sang just a few minutes ago. And we keep doing this recursively over development. So practically the bird is imitating junk. He's making junk, hearing junk, and imitating that again and again and again. What happened when you do that? Well, here is the normal song development. Here is the song development in isolation, which shows no clusters. And here is self-tutoring. And what you see in self-tutoring, you see the same pattern, even more clusters appearing, and they appear as quickly as if the bird was trained. So it's the bird's own recursive process that does that. What does that mean? It means that the recursive process of imitating yourself turns a continuous space into a symbolic space. And what's cool about that, which is of course internally driven, all dynamic interactions like that, is that the initial one is very good for learning. You have this very, very broad cloud of sounds which allow you to imitate anything. But then the second one is good for cultural transmission. So it's nice to see how the morphogenesis here serve both functions in different developmental stages. So what are the homologies between development of exploration in vocal space and local space, if there are any? Well, in both cases we see gradual growth and emergence of structure. In both cases, we see differentiation of existing primitive prototype into something more and more complex. And in all cases, we see that the recursive interaction with the environment can explain the dynamics. But I want to end by asking another provocative question. How can one explore and learn without getting lost? Now, if you think about it in terms of space, in exploration, the home base is really the safe place. And therefore, when you do those excursions back and forth, you keep yourself safe and you don't get lost. I would claim that in song, there's no safety issue, except in a cultural context. Because here getting lost means, how come the entire communication system doesn't go into conformity or into chaos? Now, I don't have time to talk about that, but I just want to show you one slide about which direction that can go. One of them, across generation, is to look at culture as something that starts with one animal, imitation by other animals, and then everyone do the same thing. Then communication means nothing. Another way is a chaotic process, where animals imitate each other, but keep changing their mind about what to do. That's the chaotic culture. But the birdsong culture, and many human culture, is in a sweet spot of having stable polymorphic culture, which can be actually cumulative and additive. This is actually what makes us human. And birds have their development designed to allow that. I don't have time to talk about it, but we did study that, and I'm happy to talk about it. In the end, I just want to end by one slide mentioning a paper that is going to be published soon, which is actually an integration of what I learned from Ilan, from Yoav, and also from Amot Zehavi. It's a paper that I did also with Arnon Lotem. And here, what we did, we actually look at the same process of dynamic interaction with environment and collective behavior in humans. Here, you know, this is the game that I did where people are practically moving in trajectories in the field. They're using ferries to go around and rating them and communicating. And by these kind of methods, we managed to put together a lot of approaches that we learned about morphogenesis of behavior, about differentiation of patterns, and interestingly enough, even about costly signaling. So that's just like a teaser to what we're trying to do now. But anyway, that's the end, so thank you so much. And,
So I am supposed to manage the discussion. So let's talk about the homology, and in biology we have the homology and analogy. And I would say that if you are claiming that these are properties that comes out of the dynamics with the environment, then perhaps an analogy would be more, or are there any suggestions that there is something that, like in the past, some common ancestor that can be traced in any way?
I don't know. I mean, my line of thinking here was to think about development of behavior as an embryology. And if you think about development of an embryo, you see prototype structure and emergence of differentiations from it. To what level does differentiation of behaviors correspond to how cells differentiate in an embryo? Is that what people would call deep homology, or just bullshit argument about homology? I don't know. There's definitely some, I mean, I always say that, you know, it could be analogy. I always say that God is lazy, right? I mean, everything in nature is recycled and redone. So I don't know really how to answer this question, but I think there's something very universal about development that would apply to different systems, even if the patterns were convergent in some sense. I don't know if it's a good answer.
Yes, it sounds to me very much like ideas of Waddington.
Yeah, I guess so. The Waddington idea. So yeah, I mean, so I guess that, how would you call it? It's some kind of, I guess, universal rules of how forces of convergence and divergence generate structure. Right, I mean.
And there are two different scenarios. One, there's like a tutor who hits on the song and imitates this tutor. The second one imitates itself. So in the first one, it's clear to me there's some kind of a tractor that pulls the system into a state. Well, in the other one, where is that tractor? What is the dynamics that drive?
Right, yeah. So the reason that we did this experiment is that we wanted really to see if you need an external attractor or you have a recursion function that actually acts an attractor. Now, if you think about what's happening here, you could think about clustering as a compression. So if you try to take a signal and compress it, you can put a grid and say, okay, this belongs here, this belongs here, this belongs here. So what I think that what's happened, you can think about it as bad memory in some sense, right? That every time you try to represent something, you remember it vaguely, and you say, oh yeah, this one was more or less here. And if it goes to the production space, you kind of lose the continuity and generate those categories. The question is how much you compress. And that's, I think, the magic here. There is an ideal level of compression that would actually work for cultural transmission and communication. And it's very, very different across birdsong species. Some birdsong will generate 200 syllable types. Those guys will generate 5 to 10. And that really depends on their biology. And this is a thing where it's interesting to try to understand the innate function and how it varies across species. I don't know if I answered, but that's probably the best I can do.
Thank you very much, Ofer.